Welcome back. We are trying to prove the Cauchy peano existence theorem, where we use only the continuity assumption on the function f. To prove the peano theorem, first we prove the existence of an approximate solution to the initial value problem. Let us recall the theorem we have stated, that is theorem 1. Consider an initial value problem dy by dx with the initial condition dy by dx is f of x y with the initial condition y at x0 is y0, where the function f is continuous on a rectangle defined by x minus x0 is less than or equal to a and y minus y0 is less than or equal to b, and we take some constants. M is the maximum value of f in the rectangle and h is minimum of a and b by m. Then the conclusion of the theorem is that there exists for a given epsilon greater than 0, there exists an epsilon approximate solution to the initial value problem on the interval x minus x0 less than or equal to h. So, we will prove this theorem now. So, the proof is that for a given epsilon, so let epsilon greater than 0 be given, and let us consider the rectangle R. So, this is a rectangle R we defined, where this side is y minus b, y0 minus b, and this side is y0 plus b. This side of the rectangle is x0 plus a, and this side of the rectangle is x0 minus a. And we are looking for a solution, approximate solution on the interval x0 to x0 plus h. The given initial point is here x0 y0 is a given initial point. Now we make polygons and join them to get an approximate shape of the solution curve. An approximate solution will be constructed, an approximate solution so by approximate means epsilon approximate, epsilon is given, solution will be constructed for the interval x0 x0 plus h, the right hand side to the given point x0, and a similar construction will define it for the left hand side, left interval, that is for x0 minus h to x0. We will prove the epsilon approximate solution to this interval x0 plus h. The approximate solution will consist of the epsilon approximate solution, the solution will consist of polygonal path starting from x 0 y 0, starting from the given point x 0 y 0, the initial point. So, it start from here, this point x 0 y 0. There is a finite number of straight line segments joined end to end to form the polygonal path. That is a graph of the approximate solution. So, what we will do is, so since f of x y is uniformly continuous on R, on the rectangle R. Rectangle R is a closed and bounded set in R2, and f is continuous, that gives f is a uniformly continuous function on R. So, therefore, this implies that for every epsilon, so we start up with an epsilon, for that epsilon greater than 0, there exists a delta. Of course, the delta will be a function of epsilon, such that f of x y minus f of say x tilde y tilde, and this difference is less than epsilon whenever x minus x tilde is less than delta and y minus y tilde is less than delta. So, this follows from the continuity, in particular uniform continuity of f on R. Now, what we do is, now we divide the interval, divide the interval on which we are looking for a solution, x 0 plus h, this interval we divide into n parts. Say x 0 is the first point, then write to it x 1 less than x 2 less than x 3, etc., etc. x n, that is the last point, which is x 0 plus h. And make the maximum of x k minus 1 for any k which is less than or equal to minimum of delta, which is delta we defined just above, delta epsilon and delta epsilon by m. So, the procedure is as follows. So, from x0 y0, the given initial point, construct a straight line, with the slope f of x0 y0, which the slope we get from the differential equation. We are starting from the point x0 y0, and we know the slope of the solution at the point x0 y0 is f of x0 y0 from the differential equation, as dy by dx is f of xy. So, you construct a straight line with a slope f of x0 y0, proceeding to the right of x0, to the right of x0 until it intersect the line x is equal to x1. So, what we do is we start from the point x0 y0, and with slope f of x0 y0 draw a straight line, let it touch the line x is equal to x1 at this point. So, we got a line segment having slope f of x0 y0. Okay, so let the line this line intersect the line x is equal to x1 at some point, say at the point x1 y1. x1 is the point right to x0, and y1 is a point at which the straight line hits the line x is equal to x1. Now, this line segment, the line segment lies inside the triangular portion, inside the triangular region bounded by the lines starting from x0 y0 with the slopes m is equal to slope m and -1. See, this line segment which we just drawn from x0 towards the right of x0, that is going up to x1, and this line segment is inside the triangular portion. This is a triangular portion, triangular region. This is bounded by the straight line having slope -m and another straight line having slope m, and another straight line having slope -m, and also by the line x is equal to x0 plus. Okay, this line is x0 plus h. So, it is a triangle formed by 3 lines, and this approximate solution, portion of the approximate solution starting from x 0 y 0 lies inside this triangular portion. And what is the guarantee that this line segment will lie inside the triangular portion? So, this follows from the definition of H, which is minimum of A and B by M, and the fact that the bound for f of x is H, is M, f is bounded by M. Now, we define solutions on each of these subintervals. Now, we define solutions. We now define approximate solution on each subinterval. In the same way. So, in the first interval, that is in the interval x 0 x 1 is a first interval, there the solution is y of x is equal to, starting from y 0 plus slope is f of x 0 y 0, and this is up to the, and x varies up to x 1. This is from x minus x 0. This is a straight line, equation of a straight line having slope f of x 0 y 0 and starting from the point x 0 y 0. This solution on the interval x 0 x 1. And similarly, so on the interval x 1 x 2, the solution is y of x is equal to, and there we start from the last point of the previous interval, which is y at x 1, which we obtained from the first solution of the first interval, y at x 1, plus the next slope is f of x 1 and the point there is y of x 1. So, this is a slope and x minus x 1. So, this is a solution defined on, it is a straight line starting from the last point x 1 x 1 y 1, that is x 1 y at x 1. And similarly, if we keep on doing on the interval x k minus 1 x k, on this interval, so y x is given by, the solution is given by y of x k minus 1 plus the slope at y k minus 1 f of y x k minus 1 into x minus x k minus 1. So, this in general is a solution on any kth interval okay, interval of 2 points xk minus 1 xk, where k is equal to 1, 2, 3, etc. So, if you join all these solutions, these are the solutions, straight lines we obtained on each of the interval, and if we join them and we get a function which is having a piecewise derivative, piecewise continuous derivative. So, the function y obtained on the interval x0 plus h is a function having piecewise continuous derivative. So, that is y is an element of C1p x0 plus h. So, in the property of approximate solution, we want the solution to be in C1p on those points at which the derivatives are defined. Now, let us consider, so for any x and x tilde, let us take 2 points x and x tilde in x0 plus h. To study further properties of y, let us take 2 points x tilde and x tilde, x and x tilde in the interval x0 and x0 plus h. Okay, without loss of generality, let us assume that x tilde is an element in one of the subintervals. Say it is in xi minus 1 xi, and x is in xj minus 1 xj, and assume that this is xi minus 1, this is xi. So, this is xj minus 1, this is xj, and we take x from here. Okay. So, x tilde is somewhere in the interval between xi minus 1 and xi, and x is from the interval xj minus 1 xj. So, consider the difference y of x minus y of x tilde y of x minus y of x tilde. This okay, we can write this as y of x minus y of xj minus 1 okay, remove this, let's write it afresh. y of x minus y of x tilde is equal to y of x minus y of x j minus 1 plus y of x j minus 1, adding and subtracting j minus 1, minus y of I plus y of xi minus y of that is consider y of x minus y of x tilde is equal to y of x minus y of x j minus 1 plus y of x j minus 1 minus etc. minus y of xi plus y of xi minus y of x tilde. If you group them, so this is less than or equal to y of x minus y of j minus 1. So remember y x j minus 1 is less than x plus etc. plus y of xi minus y of x tilde. And if you look at the properties of the solution, the function y, because y is a solution and y is a solution satisfied by the formula given, that is the equation of a straight line. So this is equal to less than or equal to m times x minus x j minus 1 plus etc. So remember the form for yx is equal to y of x k minus 1, or in this case j minus 1 j minus 1 plus f of x j minus 1 y x j minus 1 y of x is y of x j minus 1 plus f of slope is f of x j minus 1 y x j minus 1 into x minus x j minus 1. And we know that by definition this quantity is, so that is if you take the difference yx minus y x j minus 1 is less than or equal to the slope x j minus 1 y x j minus 1 into x minus x j minus 1. And this quantity is bounded by, this is bounded by m. So, therefore, we get the first term is less than or equal to m times x minus x j minus 1, and similarly the other terms are coming as a solution from the each interval. You can compute it to get this is also m times xi minus x tilde. Now, use the fact that this x1, x2, x3 they are all in the increasing order. So, therefore, this absolute value we can get rid of that. This is less than or equal to m times x minus x j minus 1 plus x j minus 1 minus etc. Minus plus x j x I minus x tilde, and we will be able to cancel out these terms to obtain m times absolute value of x minus x tilde. So, what we have shown is the absolute value of y of x minus y of x tilde, where x and x tilde are from anywhere in the interval x0 plus h, is less than or equal to a constant m times x minus x tilde. So, in particular, okay, so now, so you call this inequality as star, we will be using it again. So, in particular, let x tilde is equal to x0, the first initial point x0. Then what we have is y of x minus y of x0, which is less than or equal to m times x minus x0. So, that is absolute value of y of x minus y of x0 is y0 is less than or equal to m times x minus x0 is bounded by h, and which is again bounded by b by definition of m, by definition of h, this is bounded by m. So, therefore, what is the conclusion? The conclusion is so we obtained yx for any x minus y0 is less than or equal to b. So, therefore, this implies that x y of x, this is a point inside R for x in the interval x0 plus h. So, hence f of x y of x is defined. Y of x is the approximate solution we defined, we constructed, and f of x y x is defined for all x for x in the interval x0 plus h. Now we consider an x in the interval, say xk minus 1 xk, a particular interval. So, we get also we know that in this interval the solution y x is given by, okay. So, we have this interval, the solution is y x is equal to y of x k minus 1 plus f of x k minus 1, the slope f of x k minus 1 times x minus x k minus 1. This is a equation of the straight line or the solution defined in the interval x k minus 1 x k. Okay, obviously f prime x is a slope, is f of x k minus 1 y of x k minus 1, which we will use later. So, let us see what is y of x minus y of x k minus 1 here. Y of x, the solution, minus y of x k minus 1, the solution at the starting point. So, this is less than or equal to, if you make use of this equation, y of x minus y of x minus y of x k minus 1 is bounded by the bound of f, which is bounded by m. So, this is m times x minus x k minus 1, which is of course less than, by definition of our partition, m into delta by m, which is delta. So, that delta is a function of epsilon. Now, if you take the difference of the derivative y prime x minus f of x y x. So, in this interval, if you find the difference of this solution, the derivative of the solution with the right hand side of the differential equation, y prime x minus f of x y x, in fact, is going to be the error, the difference between the solution. So, which is equal to, we have seen that y prime x is f of x k y x k minus 1. So, this is f of x k minus 1 y x k minus 1 minus f of x y of x. And from the uniform continuity of f, we have seen that. So, this is less than or equal to epsilon by the uniform continuity of f. So, whenever x minus x k minus 1 and x, the difference between x k minus 1 x is less than delta, and y x k minus 1 and y x less than delta, this difference is less than epsilon by the uniform continuity of f. So, what does it say? So, this implies that if y now satisfies all the properties of an epsilon approximate solution. So, this implies that y x So, Yx is an epsilon approximate solution. So, y is in C1p and y prime minus y, this is less than epsilon for all points at which the derivatives are defined. So, that is not satisfied only at a finite number of points at which the derivatives having gem type discontinuity. Now, with this background, we are going to prove the celebrated theorem of Cauchy and Peano. So, Cauchy-Peano theorem on the existence of solution. So, theorem. Cauchy-Peano existence theorem. So, in the previous theorem, under the same conditions of the previous theorem, we are going to show that the initial value problem is going to have a solution. Okay. So, the statement of the theorem is let f x y be continuous on the rectangle R, which is defined as set of whole x y such that x minus x 0 is less than or equal to a, y minus y 0 is less than or equal to b. Then there exists a solution to the initial value problem dy by dx is equal to f of x y, y at x 0 is y 0. In the interval x minus x 0 is less than or equal to h, where h is so minimum of a b by m, with the m being m is equal to the maximum of the function f x y, where x y is in the rectangle. So, for all x y the rectangle, if m is a bound, is the maximum of it, then there exists a solution in the interval starting from the point x 0 y 0. So, let us quickly see the proof of it by using the ideas from the previous theorem. Proof. So, now we epsilon n to be 1 by n, where n is equal to 1, 2, 3 etc. Be small sequence of positive numbers. Now, for each epsilon n, for each epsilon n, there exists an epsilon n approximate solution. Approximate solution, call it yn x to the initial value problem. Okay. So, this is true because of our previous theorem. For every epsilon n, there exists an epsilon n approximate solution, which we denote by yn to the initial value problem. Now, by theorem, the previous theorem 1, the theorem we have shown that yx and ynx, the approximate solution ynx minus y0 is less than or equal to b, or ynx is bounded by y0 plus b. So, right hand side is independent of n. So, therefore, the family of solutions. So, therefore, this implies that ynx, the solution, this sequence of solution is uniformly bounded. So, this is a uniformly bounded sequence of functions. Again, from the previous theorem, from the previous theorem, in fact, from the inequality from star, if we look into the previous theorem, we have shown that this is star, this inequality. So, from star, that y minus yx minus yx tilde is less than or equal to m x minus x tilde for all x and x tilde in the interval x0 plus h. So, therefore, again from star we have that ynx minus ynx tilde is less than or equal to m times x minus x tilde, where x and x tilde are numbers from x0 plus h. So, what does it say? It says that, so this implies that the sequence yn is an equicontinuous equicontinuous family of functions. So, therefore, the approximate solutions epsilon n approximate solutions, which are denoted by yns. So, yns are uniformly bounded and equicontinuous. Now, we invoke Arzelà-Ascoli theorem. We here make use of Arzelà-Ascoli theorem. So, thus by Arzelà-Ascoli theorem, there exists a subsequence of yn, a subsequence of yn, say ynk. So, there exists a subsequence of ynk such that ynk converges to some function y uniformly on x0 plus h. So, invoking Arcelà-Ascoli theorem, we get a sequence, a subsequence of the constructed sequence yn that converges uniformly to some function y in the interval x0 plus h. So, this implies that y is continuous So, again by using the theorem we discussed in the preliminaries, a sequence of function converges uniformly and each y and k is continuous, then the limit function is also continuous, and y of x minus y of x tilde is less than or equal to m of m times x minus x tilde. Okay, so now our task is to prove that this limit function y is a solution to the initial value problem. So, we now prove that the limit function y satisfies the initial value problem. So, for that consider the error term. So, consider the term denoted by delta nk of x, which is equal to y nk, which is a subsequence we extracted from the sequence prime, minus f of x y nkx. So, this difference, this is error, if y prime nk exists, otherwise we take this 0, otherwise. Thus, otherwise case is only for finitely many points. So, in other words, this is y nk prime is equal to f of x y nkx plus delta nkx. Now, integrating over x0 x, we get, so integrating we get y nk x is equal to y0 plus integral x0 to x f of t y n k t plus delta n k t dt. But we know that y and k converges to y uniformly. So, this implies that as f is continuous, f of t y n k t converges f of t y t uniformly. So, uniformly as f is continuous, f is uniformly continuous. So, this implies that the integral x0 to x f of t y n k t dt converges to integral x0 to x f of t y t dt. Further, we have delta n k, which is by definition is less than epsilon n, which is 1 by n, and passing to the limit this tends to 0. So, we prove that the limit of star, the limit of star is y of x is equal to y0 plus integral x0 to x f of t y of t dt, and obviously y at x0 is y0, and by basic lemma y has to satisfy. So, by basic lemma y satisfies the initial value problem. So, therefore, the limit of this convergent subsequence y and k is a solution to the initial value problem. So, this proves that solution exists. The limit function y n is a solution to the initial value problem. So, in this lecture we have proved that if we have an initial value problem dy by dx is equal to f of x y and f is continuous with respect to x and y, then there exists a solution to the initial value problem. The uniqueness is not guaranteed. Okay.